In this video, we're going to define what an angle is and talk about how we measure these angles. Though before we even define an angle, we need to define something called a ray. So definition for us. A ray is a part of a line consisting of an endpoint and all points on one side of the endpoint. So for example, here's an endpoint, I'm going to call it P, and we indicate with an arrow that we have a line going on forever, but it's only going in one direction. And I'm just going to pick another point on this ray, I'm going to call it Q, and this denotes the ray P2, which we indicate by the 2 points, P and Q, with an arrow over the top to indicate it's a ray. Now, if you're naming a ray, the first letter always corresponds to your endpoint, and the second letter is just any other point on the ray. Now, an angle is formed by taking our ray and rotating it around its endpoint. So an angle is formed by rotating a ray about its endpoint. The starting position of the ray is the initial side of the angle, and the final position is the terminal side. Of the angle. The common endpoint is called the vertex of the angle. So I'm going to draw what I mean by all of this, but just know where the ray initially starts is the initial side, and where it is after you rotate it is the terminal side. And the point that we're rotating about, which was the endpoint of our ray, ends up being called our vertex. So let me just draw an angle for us. This is going to be my initial side, the ray AB, and I'm going to say here's its terminal side, the ray AC. We're rotating it this way, and I'm going to call that angle theta. Now, standard position for an angle the initial side is the positive x-axis. And the vertex is the origin. So if this were an angle drawn in standard position, I would have, there's my y-axis, there's my x-axis, there's my point 0, 0, my origin, and now I'm in standard position in my coordinate plane. Now, the measure of your angle theta tells us the direction that the angle is being rotated and the amount of the rotation. So the measure of an angle quantifies the direction and amount of rotation from the initial side to the terminal side. We consider a positive angle measure as being rotated counterclockwise, and a negative angle measure is when we rotate clockwise. One full rotation is equal to 360 degrees. So for example, if I have this angle here, theta, this is 45 degrees. It's positive because I'm going counterclockwise from where it started initially. And this angle that goes all the way around 3/4 of the circle, that is negative 270 degrees. It's negative because I'm going clockwise around, 270 degrees because 3/4 of 360 degrees is 270 degrees. Now, some special angles that we talk about sometimes are right angles, straight angles, acute angles, and obtuse angles. A right angle is 90 degrees. A straight angle is 180 degrees. So this quick little drawing here, if I had a right angle, if we're talking about that angle right there, going 90 degrees, 180 degrees for our straight angle, goes around like that, makes a flat line, which is why it's called a straight angle. Acute angles are between 0 degrees and 90 degrees. So an acute angle would look something like this. And then an obtuse angle is between 90 degrees and 180 degrees. So an obtuse angle looks something like this. Now, from previous classes, like if you've had a geometry class at some point, you probably know a lot of this stuff already, and you also know what complementary and supplementary angles are. But just in case, let's define those. Complementary angles are angles where the sum is 90 degrees. So it's two angles that when I add them together, I get exactly 90 degrees. Supplementary angles add up to 180 degrees. So I'm sure most of you have probably dealt with degrees before for your angles, but you might not have talked about more precise measurements of angles that are called minutes and seconds. So a degree can be divided into 60 equal parts called minutes, which we denote by MIN or like a little apostrophe. And a minute can be divided into 60 equal parts called seconds. Which we abbreviate by just SEC or a double apostrophe. So we know that 1 minute equals 1/60th of a degree, and 1 second is equal to 1/3600th of a degree. Those are our conversion factors to go from degrees to minutes and seconds. So let's do a quick couple examples converting between decimal degrees and minutes and seconds. Let's convert 131 degrees, 12 minutes, and 33 seconds to decimal degrees, to 4 decimal places. Well, I want this all to be in degrees instead of degrees, minutes, and seconds. I want it to say 131 point something degrees. So let's see what we have. I have 131 degrees. I have 12 minutes. And 12 minutes would be 12 out of 60 degrees. And 33 seconds is 33 over 3,600 degrees. That's just using all of my conversion factors. So now let's just see what we get when we convert this into decimals. I have 131 degrees plus 0.2 degrees. And this last guy is 0.009166, and the 6 just repeats forever, degrees. So adding this up and rounding it to just 4 decimal places, I get 131.2092 degrees. All right, so that's how we convert from the degrees, minutes, seconds notation into decimal degrees. But what if you're given a decimal degree and have to convert it to degrees, minutes, seconds? Well, let's do an example going the other way. Let's convert 26.48 degrees to degrees, minutes, seconds form. Well, what I know so far on this is I have 26 degrees plus 0.48 degrees. Well, let's see what 0.48 is in terms of minutes. Well, this is going to be equal to 26 degrees plus 0.48 times my conversion, 60 minutes for every 1 degree. Notice then my degrees would cancel out and this would convert it into minutes. So I have 26 degrees plus 28.8 minutes. Well, that put it in degrees and some minutes, but I still have a fraction of minutes, so that's going to get me some seconds. So I have to change this 0.8 minutes into seconds. Right now I have 26 degrees, 28 minutes, and 0.8 minutes. So now we just have to convert that 0.8 minutes into seconds. How do we do that? We use a conversion factor. So I have 26 degrees plus 28 minutes plus my 0.8 minutes times my conversion factor. How many seconds are in 1 minute? 60 seconds per 1 minute, and I multiply that out. 26 degrees, 28 minutes, and then the 0.8 times the 60 gets me 48 seconds. So writing that angle in degrees, minutes, seconds, I get 26 degrees, 28 minutes, 48 seconds. And so now we know how to convert between the degrees, minutes, seconds notation and the decimal degrees notation, and going back again the other way. Let's move on to another definition. A central angle is an angle with a vertex at the center of a circle. A central angle that intercepts an arc on the circle with the length of the arc equal to the radius of the circle has a measure of 1 radian. So far we've only been talking about angles in terms of degrees, minutes, and seconds. Radians are another way of measuring angles. And quite frankly, in mathematics, we use radians way more than we use degrees. But it's important to be comfortable with both degrees and radians because there's a lot of applications out there that prefer to use degrees. So you should be comfortable with both of these. So we have our formal definition of what a radian is. Let me just draw a picture of what it's talking about. This is an approximate picture. If I have a circle, and I'm talking about a central angle, here's my angle theta. This is the radius of my circle. And this distance here, I'm going to call S, is the arc, the measure of that arc. If S equals R, then theta is equal to 1 radian. Now, of course, my picture's not drawn perfectly to scale, but we're saying if this radius is the exact same distance as that curve, then that angle is equal to 1 radian. The radian measure of a central angle theta subtended by an arc of length S on a circle with radius R is theta equals S over R. So if the S and the R are exactly equal to each other, that's when we have a measure equal to 1 radian. But this formula gives us the angle measure for any amount of radians. It's the ratio of the arc length S to the radius R. One full rotation when using radians, instead of calling it 360 degrees, we say it's 2 pi radians. One full rotation is 2 pi radians. And for example, this angle here that goes halfway around the circle, this angle is pi radians, which is 180 degrees. And our right angle, we know that's 90 degrees. In radians, this is pi over 2 radians. So of course, if we have all these different ways of measuring angles, we're going to need to be able to convert between degrees and radians so that we're comfortable with what we're doing. So here are our conversions. If I'm going degrees to radians, we need to multiply by pi over 180 degrees. And if I'm converting from radians to degrees, we multiply by that reciprocal, 180 degrees over pi. And this will convert us back and forth between degrees and radians. So, for example, let's just do a couple quick conversions. Convert 300 degrees to radians. Well, to convert 300 degrees to radians, I need to multiply it by pi over 180 degrees. And you know which version to use, whether it's pi over 180 or 180 over pi, because you want to have your units cancel out. So my degrees will cancel out, leaving it in terms of radians. So this gets me 300 over 180 times pi, which if I simplify that fraction, I get 5 pi over 3 radians. And now let's go the other way. Let's convert negative 7 pi over 4 to degrees. Well, I would take negative 7 pi over 4, and if I'm converting it to degrees, that means I need the degrees on the top, radians on the bottom, and multiply this out. And that will get me negative 1,260 over 4 degrees, which if I simplify that fraction is negative 315 degrees. So converting back and forth between the two really isn't too bad as long as you remember your conversions. To convert from degrees to radians, multiply by pi over 180. To convert from radians to degrees, multiply by 180 over pi. Another definition for us. Two angles in standard position with the same initial side and same terminal side are called coterminal angles. quick example of what that looks like. Let's just say that's my terminal side. So I have this angle here, theta. An angle that's coterminal to that, well, I could go all the way around and then back to this terminal side. Let's call that big angle. I guess we'll call that one alpha. Alpha and theta are coterminal angles because their terminal side is the same. It's just that alpha went all the way around and then went back to the same place. Now, coterminal angles always differ in measure by a multiple of 360 degrees or 2 pi radians. So they always differ in measure by a multiple of 360 degrees or 2 pi radians. And that's just like in the drawing I had, because we have to go all the way around the circle in order to get back to the same terminal side. So your coterminal angles will always differ by just full rotations around the circle. So let's start by finding a coterminal angle to a particular angle theta. Find an angle coterminal to theta equals 1,230 degrees between 0 degrees and 360 degrees. So first notice my 1,230 degrees, that is way bigger than one rotation around the circle. So I'm going to want to subtract a multiple of 360 from this angle in order to find a coterminal angle that fits within one revolution around the circle. So let's figure out how many revolutions I have to subtract off. I know if I go around the circle one time, that's 360 degrees. If I go around twice, 720 degrees. 3 times is 1,080 degrees. And if I were to go 4 times around a circle, I would be at 1,440 degrees. Now, the angle that I have, 1,230 degrees, is in between 3 times around and 4 times around. So I don't want to subtract 4 times 360 because I'll end up getting a negative angle overall. But I can subtract my 3 times 360, and that would get me my coterminal angle that I'm looking for. So I have my 1,230 degrees minus 3 revolutions, which is 1,080 degrees. That is equal to 150 degrees. And that is a coterminal angle to my 1,230 degrees. So it's just a matter of either adding or subtracting a multiple of 360 degrees until you get to the correct answer in a certain range that you're given. Let's do an example in radians. Find an angle coterminal to theta equals negative pi over 8 on the interval 0 to 2 pi. So I want my coterminal angle to be in just one revolution around the circle again. Since I'm working in radians, I have to add multiples of 2 pi. I know I'm going to be adding multiples instead of subtracting because my angle's starting out negative. So I need to add stuff to it to end up getting a positive angle measure for my coterminal angle. Well, this one's a little easier than the last one because I'm just going to add 1 revolution around my circle, so 2 pi radians, and that gets me 15/8 pi radians as my coterminal angle. This is between 0 and 2 pi because 15/8 is just a little bit under 2, so it is in this interval here. All right, so what else can we do with these angles that we're learning about? We have a definition about finding the length of an arc. So given a circle of radius r, the length s of an arc intersected by a central angle theta in radians is given by the formula S equals R times theta. Notice that's the same formula we had for figuring out the angle measure in radians. It's just solved for S instead of solved for theta. Now, it is very important in this definition, our theta is given to us in radians. So if you're supposed to be trying to find an arc length from an intercepted central angle like this, and they give you the angle in degrees, the first thing you have to do is convert to radians before you can use this formula. Let's do an example using this formula. So, example. Find the length of the arc made by an angle of 220 degrees on a circle of radius 9 inches. Well, my formula for finding the length of an arc is S equals R times theta, but theta has to be in radians, not degrees. So let's first figure out our angle in radians. We have to convert our 220 degrees to radians by multiplying by pi over 180 degrees. When I multiply that out, I'm going to get 11 pi over 9 radians. Then I can use my formula. The measure of the arc is equal to R times theta. My radius is 9 inches. My angle in radians is 11 pi over 9. And so I get the measure of that arc is 11 pi inches. So remember, when you're using these formulas, you have to make sure you have the right units to begin with. We need to have the angle in radians in order to use this formula. If you just use the degrees, you're not going to get the same answer. Other things we can do using our angles, we can find angular speed and linear speed. A definition: if a point on a circle of radius r moves through an angle of theta radians in time t, then the angular speed of the point is given by omega equals theta over t. And the linear speed is given by v equals s over t, where s is talking about the measure of the arc. So we know s is equal to r times theta over t. And then another way we can write this, using this omega is theta over t, our linear speed equals our radius times our angular speed. So that's a pretty long formula there, but it's all equivalent definitions. Your linear speed is the measure of the arc over time. That's the same thing as your radius times the angle over time, which is the same thing as your radius times your angular speed. So let's do an example where we need to find these different types of speed. A bicycle wheel rotates at 2 revolutions per second. First thing we're going to do is find the angular speed. So how fast is a point on this bicycle wheel moving around an angle? Well, I know my angular speed is supposed to be omega equals the measure of my angle over the time. And you might be a little confused. What's the measure of my angle? Well, here's our clue. It goes 2 revolutions every single second. How many radians are in 2 revolutions? Well, 1 revolution is 2 pi radians. So 2 revolutions is 4 pi radians. So I'm going 4 pi radians, 2 revolutions, every second. So it's 4 pi radians per second. Now for part B, how fast does the bicycle travel in feet per second if the wheel is 2.2 feet in diameter? Round to the nearest tenth. Well, I know a formula for my linear speed. My linear speed is equal to my radius times my angular speed. And we just found my angular speed was 4 pi. But what's the radius of this wheel? Well, I know the diameter is 2.2 feet, and the radius is half of that. So my radius is 1.1 feet. So my linear speed is 1.1 feet times my 4 pi radians per second. And this gives me, if I type it into a calculator and round, 13.8 feet per second. So this is talking about how fast the bicycle is moving on the ground. The angular speed is talking about how fast the wheels are rotating. All right, we have one more definition for this video and one example using it. And then that's it for this introduction to angles and their measure. So last definition. The area A of a sector of a circle with radius r and central angle theta in radians is A equals 1/2 r squared times theta. So again, this formula has our theta in radians. So it's important that your angles are in terms of radians before you try to use this formula. Now, what is a sector of a circle? So you can understand this definition. If this is my circle, a sector is just talking about a slice. So let's just say this is my sector here. Think about slicing up a pie. One slice of pie is equal to a sector of the circle. And now we have a formula for calculating the area of your slice of pie. Let's do an example using this formula. A sprinkler rotates through an angle of 120 degrees and sprays water a distance of 30 feet. Find the amount of area watered to the nearest whole unit. Well, first, we know that our formula for the area of a sector requires radians and not degrees. So we're going to have to take this 120-degree angle and convert it into radians before we can use the formula. My angle is 120 degrees times pi over 180 degrees to get it into radians. When I simplify this fraction, I get 2 pi over 3 radians. So now I can find the area of this space that's being watered by the sprinkler using my measure 2 pi over 3 radians, and I have the distance of 30 feet. That's talking about the radius. So we have the area is equal to 1/2 radius squared times theta. So for my problem, my radius was 30 feet. My theta is 2 pi over 3. When I multiply this out, I get 300 times pi square feet, which rounded to the nearest whole unit is 942 square feet. All right, and that's all I have for you today. If you have any questions, feel free to drop them below. If you're a current student, you can also ask in office hours or through email. And next time, we're going to talk a little bit more about trig. We're going to learn our trig functions using right triangles. So I'll see you guys next time.